This lesson is about Newton's law of gravity. Now, at first glance, it doesn't seem that gravity has much to do with circular motion. And there are certainly cases in which gravity is not related to circular motion. But what we'll see toward the end of our lesson on gravity is that, in fact, it is related to circular motion of things like satellites and the moon orbiting the Earth and the Earth orbiting the sun. Well, back when Newton was first developing his law of gravity, we didn't know, nobody had any idea that gravity was related at all to the moon's orbit around the Earth or the Earth's orbit around the sun. Nobody knew why the moon orbited the Earth or the Earth orbited the sun. We knew about gravity, right? We knew that if you drop a rock, it'll fall because of gravity, but nobody had any clue that gravity was related to other things like astronomy. Gravity seemed to be an earthly phenomenon. But it was Newton who first realized that these things are tied together. Okay, that all objects with mass attract each other gravitationally. So not just the Earth and a rock, but the Earth and the moon, the sun and the Earth, and for that matter, even two people that both have mass attract each other gravitationally. Now, Newton also discovered that attraction or force between two objects with mass was proportional to the product of the two objects' masses, and inversely proportional to the distance between them, r squared. If we want to replace proportional to with equal to, then we need a constant of proportionality, which we'll symbolize with a big G to distinguish it from little g. Okay. And G is called Newton's gravitational constant, or the universal gravitational constant. It's equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Now that's a pretty small number, and it's that small number that explains why it is that you haven't noticed being gravitationally attracted to a person sitting next to you. Let's use this equation to find the force of gravity between, say, a 70 kilogram person and maybe a 80 kilogram person, not an 800 kilogram person, an 80 kilogram person sitting next to each other, say on a couch. Let's say they're sitting next to each other on a couch just 30 centimeters apart. Okay, so we'll see F is equal to big G, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times M1 and M2. Now it doesn't matter which one you put first, okay, because M1 times M2 is the same thing as M2 times M1. 70 kilograms times 80 kilograms, all divided by the distance between them, 30 centimeters, or 0.3 meters squared. Okay, now if you look at the units, we have kilograms squared here, which cancels those kilograms. You have a meters squared here, which cancels that meters squared. Along with me with your calculator to make sure that you can type all of this in correctly. So we have 70 times 80 is 5,600. We'll divide that by 0.3 squared, which is 62,222. Then we will multiply that by 6.67 times 10 to the minus 11. And that gives us 4.15 times 10 to the minus 6. 4.15 times 10 to the minus 6. And we're left, the only unit that didn't cancel is newtons. So about 4 micronewtons. Compare that to the weight of one of these people, right? The 70 kilogram person has a weight of 70 kilograms times 9.8 meters per second squared, or what about 686 newtons. All right, so the force of gravity between you and somebody sitting next to you on the couch is about 100 million times less than the force of attraction between you and the Earth due to gravity. So that's why you've never noticed it before. But it is there, nevertheless. By the way, speaking of the weight of a person, one way to determine the weight of a person is just to take that person's mass and multiply it by little g, 9.8 meters per second squared. But we could also determine the weight of a person using Newton's law of gravitation. Let's do that. There are a couple of things that I want to show you in working that example out. Okay, so I'm going to delete the example that we just worked. Now let's find the force of gravity between the Earth and a 70 kilogram person using Newton's universal law of gravitation. F equals 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Okay, now M1 will plug in the mass of the Earth. So if you don't know the mass of the Earth, and actually I don't know the mass of the Earth, then you can look that up in the front cover of your textbook, or you can ask Google, which I will do. According to Google, the mass of the Earth is 5.97 times 10 to the 24 kilograms. 5.97 times 10 to the 24 4 kilograms. Okay, that's M1. M2 will be the mass of the person. 70 kilograms in this case, about 150 pounds. Divided by r squared, where r is the distance between the Earth and the person. Now here we have an interesting question. Exactly what r should I use? Because here is the Earth, and here is the person, tiny little dot up there on that scale, just a tiny little dot. So if you think, well, the person's feet are touching the surface of the Earth, so perhaps the distance should be 0. But if we put 0 there in the denominator, then dividing by 0 gives us infinity, and the person definitely does not have an infinite weight. So what distance should we use? Well, it turns out that the distance we should use is the distance from the center of mass 1 to the center of mass 2. In this case, the center of mass 1 is the center of the Earth, and the center of mass 2 would be up to the center of that person, but of course that distance is essentially 0 compared to the radius of the Earth. So in this case, the appropriate distance between the person's feet, or the center of the person, and the center of the Earth is simply the radius of the Earth. So we need to plug in the value for the radius of the Earth in the denominator and square it. So once again, look that up in the front cover of your textbook or ask a Google. The radius of the Earth is 6.38 times 10 to the 6 meters. 6.38 times 10 to the 6 meters. And we need to square that. Okay, I'm going to stop here before we multiply all that together and talk about the fact that you should use the center of mass, or the center of the Earth, to the center of the person. When Newton first published his theory of gravity, he wasn't sure, or actually I should say when he first developed his theory of gravity, he wasn't sure that the center of the Earth to the center of the person was the correct way to measure that distance. His intuition told him that that was correct, but he couldn't prove it. The reason he couldn't prove it was because in order to prove that, you need calculus, and calculus hadn't been invented yet. So Newton didn't publish his theory of gravity right away. Instead, he invented calculus, used it to prove that the center of the Earth was the correct place from which to measure the distance, and then he published his theory of gravity. So that's kind of impressive, I think. All right, now now we can go ahead and multiply out the numbers in our example. But if you're working through this on your own calculator, I recommend that you do the part that I have circled first before you multiply it by the 70 kilograms. And if you do so, then of course what you are going to determine is that all of that stuff in the circle is simply 9.8 meters per second squared, or what we call little g. Okay, so now you know where little g comes from. It comes from Newton's universal law of gravity. So as long as you stay on the surface of the Earth, then the acceleration of gravity is 9.8 meters per second squared. If we go to a different planet, that has a different mass or a different radius, you'll have a different value for little g. Or, for that matter, if you get substantially far away from the surface of the Earth, then the Earth's radius would no longer. All right, I'm going